Thank you for joining us today. We have our next to the last What Physicists Do of the semester. It's coming down to the wire, but I'm really happy that we have Dr. Tesla Jeltema today. I found out today, I was like, oh, it's a lovely name. And then I thought, well, Tesla, it has occurred to me that that's not that common. And in physics that we are very familiar with this name. And so I asked if she was named after the scientist. And she has the best line of all. She says, no, I was named after the unit of measurement. Right?
My mother was a grad student at the time.
Well, she's a professor at UC Santa Cruz. Her work is focused on investigating dark matter and dark energy. That's why we're all out here today. And often by studying clusters of galaxies. She is a key contributor to the Dark Energy Survey and is involved in planning the Large Synoptic Survey Telescope, the LSST. Her bachelor's degree in physics is from the College of William and Mary. Her PhD is from MIT, and she spent a postdoc at Carnegie and is now at UC Santa Cruz. Let's give a warm welcome to Dr. Tesla Jeltema.
Thank you for having me here today. So yes, as Scott kindly introduced, I'm a faculty member at UC Santa Cruz. I work in the field of astrophysics, and in particular, my interests are in understanding what is the nature of dark matter, of dark energy, how much dark energy is in the universe, how is the universe evolving. Much of my work concentrates on using the formation of structure in the universe, so galaxies and, as I'll tell you today, massive clusters of galaxies to probe the nature of those dark components of the universe. So what I'm going to talk about today is some of my work with the Dark Energy Survey. But before I get to that, I wanted to give first a picture of what we think the history of the universe was from the Big Bang to today. And then, because I like the scientific method, I'm actually going to step back before I talk about current research and give you a little bit of a history on how we came to that picture. So some of the key observations that led us to the picture we have of the evolution of the universe and the formation of structure. And then I'll talk to you about our current work in trying to understand more about dark energy, or more generally, the fact that the expansion of our universe is actually accelerating, which is quite cool. Okay, so I start with this woodcut that I love that pictures a monk peering through the heavens to see the machinery with which it works. Okay, so this slide shows two versions of the history of the universe from the Big Bang to now. This one on the left I call the particle physicist version of this picture because it emphasizes the really very early universe and all of the transitions in particle physics and fundamental forces that happen really early on. And this is the astronomer's version of the history of the universe, which emphasizes the things that we can actually observe. Okay, so the universe is about 13.8 billion years old. Started with what we call the Big Bang. And that very early universe we really don't know much about. There's a limit to how early we can model because eventually the universe becomes so small that we need quantum gravity, which we don't yet have. But what we do know is that the early universe was extremely small, extremely dense, and extremely hot. So hot, in fact, that it was filled solely with radiation, just with photons, just with light. It was too hot even for bound particles. So following the Big Bang, the universe expands and cools over that 13.8 billion years. And so as it cools, there are several kind of phase transitions that happen. So after about a microsecond, the universe is cooled to the point where particles can form. So, we start having things like neutrons and protons. And then after a couple of minutes, so again, we keep expanding and cooling. After a couple of minutes, the universe is cooled to the point where it's cool enough that neutrons and protons can bind into nuclei. So now we have nuclei, but it is still so hot that we don't have neutral atoms. So at this point, the universe is a soup of radiation and positively charged nuclei and negatively charged electrons. So it's a very hot plasma. And so that expansion and cooling continues until we get to, well, it's continuing even till today, but eventually at about 300,000 years after the Big Bang, we get to the era of the cosmic microwave background. So that the era that we're observing when we see the cosmic microwave background. So this is what we call recombination. It is the point at which the universe has cooled enough that now electrons can bind to nuclei to form atoms. So at that point, the universe becomes neutral. And what's important about that is that before that, when we had everything was ionized, the photons, the light, was always electromagnetically interacting with all of the charged particles and charged nuclei around. But after we form neutral atoms, the photons are free. So they just free stream from that point to us today. And it's that radiation left over at this epoch of recombination that we now observe as the cosmic microwave background. So again, as the universe expands, it cools. So at this point, that leftover radiation from the Big Bang is at a temperature of 2.7 Kelvin. So just a little bit above absolute zero, but above absolute zero. And that's what we measure when we measure the cosmic microwave background. But those photons, that light has come basically straight to us from this epoch 300,000 years after the Big Bang, and it allows us to observe what the universe looked like at that time. Now, the first stars and galaxies and structure don't start forming until about 500 million years after the Big Bang. So all of the wealth of galaxies, stars that we see today didn't start forming until quite a bit after this. Okay, so that's the basic picture. So in trying to understand the expansion of the universe, a lot of people use a blowing up of a balloon analogy, but I like the baking raisin bread analogy. So here, what you want to imagine is that our universe is a ball of raisin bread dough, and the galaxies the galaxies here are the raisins. So the galaxies are the raisins, and then I put my raisin bread dough in the oven and I heat it, and the dough will rise. So it's not that the galaxies themselves, this is just a very simple cartoon animation, so see, it rises. So here are my galaxies. It's not that the galaxies are physically like moving away from each other, it's that the amount of space in between them is getting larger. So the amount of space in between them is getting larger. And as you see, so this is so we have a local raisin. So this is another cartoon. So what that means, though, is that the farther away a galaxy is from us, the faster it looks like it's moving away from us. It's not physically traveling. But so, here, if I have a raisin that's 1 centimeter from me, and then I have a different raisin that's 3 centimeters from me, and if if in some amount of time, the amount of space increases by a factor of 3, this one looks like it's gone an extra 2 centimeters from me, but this one that was 3 centimeters is now 9, right? So this one appears to have moved away from me faster than this one, but it's that the amount of space in between is increasing. Okay, so that's the cosmic expansion. Now, in the midst of that cosmic expansion, all the wealth of structure that we see is forming. So this is going to be a computer simulation. So this is my universe in a box. You see my box. I'll run the movie in a second. In that very early universe, the universe is almost exactly the same everywhere. You can't really see any difference here. But it's not precisely the same. It's very, very close to the same everywhere, but not quite. So as the universe evolves, if I have a part of the universe that has a little more mass, so it's a little denser, that region, because of the attraction of gravity, is going to pull together. So the matter is going to pull towards those overdense regions. And then if I have a region of the universe that has less density, stuff is going to be pulled out of it. And what that means, so I'm going to run my movie now. Oops, no. Movie. What that means is that you get the overdense regions becoming even more dense and the underdense regions becoming even less dense. And you form what we call the cosmic web, this filamentary structure, and here each little dot would be a galaxy. So this very complicated large-scale structure that we actually observe in the universe. Okay, so this is then a snapshot of one of these large simulations and then zooming in. So what you get is this immense cosmic web of structure that include things like clusters of galaxies, which is one of the types of objects I study. These are the most overdense rare regions in the universe. They live at the intersections of filaments. So a cluster of galaxies, a massive cluster of galaxies, total will weigh 10 to the 15 times the mass of our sun. It'll have thousands of galaxies orbiting in the same gravitational potential, but most of this mass is in dark matter. And then you get also enormous voids, relatively empty regions that we call voids, those underdense regions of the universe. So that structure is collapsing at the same time that the universe is expanding. And as I'll tell you, that allows us to probe what the universe is made of. Okay, so this is my universe pie chart. Probably you've seen one of these before. So what I'm going to call ordinary matter, neutrons and protons, the stuff that we're made of that we know and love, only makes up about 5% of the energy density of the universe. Most of the mass, the matter in the universe, is in dark matter, but that's still only a quarter of the energy density of the universe. Most of it is in this unknown component, which we call dark energy. Could be that the vacuum of space has a very tiny energy density associated to it, but really we don't know. So this is one of the things we're trying to learn more about. Okay, so that's what we think the evolution of the universe is, and what we think in general it is made of. So this is the point where I'm going to step back and give you a little bit of history of some of the key observations that brought us to this picture, and then moving forward how we're going to learn more. Okay, so I'm going to step back a little over 100 years ago. So my husband likes old books. We used to have this wonderful bookstore that unfortunately closed down in Santa Cruz that sold used books. And at some point, he found this set of Encyclopedia Britannica in this bookstore from 1911. So besides taking up space in my house, one of the things I liked about this set of Encyclopedia Britannica was that I got to put together this slide. So the Andromeda Galaxy is the nearest large galaxy to us. There are some dwarf galaxies, but it's the nearest large galaxy to our Milky Way. But in 1911, when this encyclopedia was written, it was not known that the Andromeda Galaxy was outside of our own galaxy. So in fact, if you look up galaxy in this encyclopedia, there's nothing because it's just our galaxy. So instead, you look up Andromeda and it's the Andromeda Nebula. So it's thought to be a cluster of stars within our own galaxy. Now this is the picture of it in the Encyclopedia Britannica. It looks a lot like a modern picture of the Andromeda Galaxy, right? And you can even pick out some of the dwarf galaxies orbiting Andromeda. But yes, but this was thought to be just part of the Milky Way galaxy. So in fact, in 1920, there was what was called the Great Debate between Harlow Shapley and Herbert Curtis as to the origin of these nebulae. So Shapley contended that these were really just clusters of stars within our own Milky Way galaxy. And there was evidence on that side of the debate. In particular, if Andromeda was outside of our Milky Way, it would have had to be enormously farther away than anybody had ever thought in terms of distance scales in the universe. They also observed nova, so brightening of stars in Andromeda that if it was at that distance would have been extraordinarily luminous. They didn't know about supernova yet, so they knew instead about more standard nova within our own galaxy that were not that bright. And so there was evidence on the side of these are part of our Milky Way. Now Curtis, on the other hand, thought that these were galaxies outside of our Milky Way galaxy. He called them island universes. And there was evidence on his side as well. In particular, the rate of nova within the Andromeda Nebula was higher than the rate of nova within the whole rest of the Milky Way galaxy. So why would this one little star cluster in our galaxy have more of these nova? And there were other arguments. So they both had rational arguments on either side, and I think this is a great example of how science happens. I mean, we have a question, we have evidence, we examine the evidence. If it's unclear, we go and design experiments and gather more evidence. And eventually, of course, Curtis was proved correct. The Andromeda galaxy is a separate galaxy, as were several other nebulae that had been discovered at the time. But Shapley was correct in other aspects as well. So, for example, he correctly said that the size of the Milky Way was larger than previously thought, and that our sun is in the outskirts rather than near the center of the Milky Way. So, that was the great debate. Okay, so how did we finally understand that external galaxies were not part of our own? Well, one of the fundamental things came with our ability to measure distances, which was really due to Henrietta Leavitt. So before Henrietta Leavitt's discovery, which I'll tell you about, the only way we could measure distances to, say, stars was through parallax. So we have a baseline of the orbit of the Earth around the sun. So say we're on one side of the sun, and you look at a star and you see its position. And then you wait 6 months, and we're on the other side of the sun, and then you have a different, triangulation to that star. It looks like it moves. And so the amount by which it moves tells you its distance. It allows you to get that distance. But as you can imagine, that is not an easy measurement to make. So there was a limit on how far away we could measure absolute distances. So what Henrietta Leavitt discovered, so she was working as a Harvard computer, which was, her job was to look at photographic plates of astronomical observations night after night after night and catalog the things that she saw. And what she found was that there is a class of variable stars, these are called Cepheid variable stars, that got brighter and dimmer with very regular periods. And in fact, the rate at which they got brighter and dimmer corresponded to their absolute luminosity, so their absolute brightness. So, if it took longer to get bright and dim and bright again, then it was a brighter star. And if it had a shorter period, so it did that process quicker, it was a fainter star. And so the calibration of this meant that we could measure absolute distances to much farther away. Because, if I know how absolutely bright my source is. So I have a light bulb, and I know the wattage of my light bulb, and I put it at the back of the room, and then I see, okay, how bright does it look to me? And I know how bright it actually is. Then I can figure out how far away from me it is. And so suddenly we could do this for these type of variable stars, Cepheid variable stars. And in 1924, so 4 years after that great debate, Hubble used he found a Cepheid variable star in Andromeda, and he was able to use that to show that the distance to Andromeda was much larger than the size of the Milky Way, so proving that it was outside of our Milky Way. So this is a scan of that Hubble plate. So you can see he was looking at nova, so he was studying these nova, so and these marking nova, and then he was following them up night after night, and he had an N here that he crossed out and wrote var, because he discovered it wasn't a nova, it was actually a variable that turned back on again. So Hubble did his observations at the Carnegie Observatories where I was a postdoc, and they actually in the basement have all of the original photographic plates of years and years of observations. So I actually got to touch this plate. I'm kind of clumsy. Why they let me hold it, I don't know, but I did actually get to hold this Hubble plate, which was really cool. Okay, so this proved that there are galaxies outside of the Milky Way. So Hubble went on to measure then the absolute distances to many galaxies, along with his assistant Humason. And using that absolute distance, using these Cepheid variable stars, and then the speed at which they looked like they were moving away from us. So this is from redshift. It's from the shifting of the light. I can tell you more about that if you want. But so he found that the farther away from us a galaxy was, the faster it appeared to be moving away from us. And basically everything was moving away from us, not random, like some things moving towards, some things moving away. And if you remember my raisin bread, this is exactly what you would expect for an expanding universe. So Hubble's observations then showed that the universe is expanding, which might sound a little weird, but in fact, actually Einstein and the other theorists of the day were quite happy because they had to go through some machinations to make the math work to make the universe static, whereas an expanding universe was more natural, and he got to throw away his cosmological constant that we have now brought back. Okay, so this survey of galaxies and how quickly they were moving away from us showed that the universe is expanding. So that was a handful of galaxies. This is what some more modern galaxy surveys look like. And you can see, so each little dot here is an actual galaxy and its position on the sky. So we've now measured the distances to millions of galaxies. And you can see visibly that they actually do follow, thank you, that cosmic web, just like those simulations that I showed you. So this is just drawing a picture of where galaxies lie. Okay, so what about the Big Bang? So in 1963, Penzias and Wilson were working for Bell Laboratories, and they discovered the cosmic microwave background. Now, they didn't aim to discover the cosmic microwave background. What they were trying to do was survey microwave noise for Bell Labs, so they would know the background to their instruments. But what they found was no matter where they looked on the sky, there was a constant microwave signal from everywhere that was almost exactly the same. And was at a constant temperature of about 2.7 Kelvin. And so this was pretty quickly interpreted by Dickey as the radiation left over from the Big Bang. Because the theory actually already existed. Because once you see that the universe is expanding, it's fairly natural to ask, okay, what happens if I go backwards, I dial backwards to the beginning? And so it was realized that there would be this leftover radiation. And so this was correctly interpreted as that leftover radiation from the Big Bang. And this is what it looks like. This is probably not the picture of the cosmic microwave background you are used to seeing. What you were probably used to seeing is this one. So, as I said, I showed you a simulation of that growth of structure for something that was almost exactly the same everywhere to the cosmic web today. So remember the cosmic microwave background, this is at about 380,000 years after the Big Bang. And so this is what you see when you subtract off this constant background. So it's almost exactly the same everywhere, but not quite. There are slight fluctuations, and these fluctuations in the temperature of the microwave background tell me that there's areas that are more dense and areas that are less dense. But this is only 1 part in 100,000. So the cosmic microwave background is the same everywhere to 1 part in 100,000. And if you can subtract it off that precisely, you can see that there are very small fluctuations. And these very, very teeny differences in density, dialed forward to now 13.8 billion years after the Big Bang, is what forms the large-scale structure that we see in the universe. So this growth of structure, along with the fact that the universe is expanding at the same time, allows us, this allows us a probe of our cosmological models, as I'm going to say, because this obviously depends on how much matter there is in the universe. That depends on the gravity pulling in. Depends on dark energy, because that affects the expansion rate, how fast that expansion is going. And so this baseline of how this structure comes to look like this today is what allows us to probe our cosmological model. And they should match if we have the model right. Are there any questions before I move farther? My end of my history lesson. Yeah.
Where do you get those numbers, like 5%?
Yeah, so I'll have us pause for a couple of slides, and I'll show you. It's a combination of observations. Yeah.
Earlier you said that other galaxies were orbiting the Andromeda galaxy. Can you explain that a little more? Like how they're orbiting them?
Yeah, so, and we actually have a number of these are small galaxies orbiting the Milky Way as well. So, that structure forms on all scales, from like really big things to really small things. And, gravity pulls things together. So we have around our Milky Way and Andromeda also these small galaxies that we call dwarf galaxies. And the mass of our Milky Way, for example, is enough that they then orbit around our Milky Way in the same way that planets orbit around the sun. If they get too close to us, they actually get like stripped. So we actually have within the Milky Way what are called stellar streams that are the remnants of galaxies that we have ripped apart. But yeah, so it's basically just gravity, and there were these small things that formed near us, and then they got trapped orbiting. Okay, so dark energy. I just like the title of this paper, Mystery of the Millennium. So dark energy, so if all we had in the universe, so the Big Bang starts this expansion, right? So the Big Bang starts the expansion at some rate. The universe is getting bigger with some rate. And if all we had was matter, if all we had was mass, then that expansion would slow down over time because gravity pulls in, right? Now, there's a question of whether or not we have enough mass that we would ever make it collapse again. But separate from that, it would certainly slow down. It turns out that expansion is actually getting faster. So dark energy, it's like an anti-gravity. It's pushing out. It makes that expansion go faster. So this is a little cartoon of Big Bang, and then the universe gets bigger, but the rate at which it's getting bigger slows down. So here's cosmic microwave background formation of structure. But then at some point there's a transition where dark energy starts to dominate that expansion history, and it starts getting faster and faster. So the accelerating universe, the fact that the expansion of the universe is getting faster, was discovered in 1998 with the measurement of the distances to supernova. So I talked about the Cepheid variable stars. So supernova are hugely luminous, explosions of stars when they die, or explosions because I have a compact object that rips apart a star near it. And there's a type of supernova called supernova 1A that are called standard candles. Now a standard candle would be, they are all exactly the same brightness, and therefore again I observe it from some distance, I see how bright it looks to me, I know how bright it actually is, and I can measure distances. They're not actually standard candles, they are what I call standardizable candles. They're not exactly the same luminosity, however they do have a very standard pattern of, amount of time till they get to their peak brightness, and then amount of time until they get dimmer again. And that amount of time it takes to get brighter and then dimmer is a measure of how absolutely bright they are. So very similar to Henrietta Leavitt's Cepheid variable stars, it gives us a way to measure absolute distances to much farther away, to billions of years in the past. And so two independent teams in 1998 published their results showing that, so this is just, it's actually flipped. This is distance versus velocity in some units. Like the Hubble diagram that I showed you from Hubble's observations, and showing that actually this isn't linear and it's not slowing down, it's getting faster. So the expansion, things are farther away than we thought they should be. So the expansion of the universe is actually getting faster and faster. It's accelerating. Another reason to think that we are missing some energy component of the universe comes from that pie chart. I didn't explain the pie chart, but comes from that pie chart, which is that we can figure out how much total matter there is in the universe from, for example, the formation of structure, right? Formation of structure tells us about how much gravity, how much mass is pulling in. So as I will tell you about, if we count up the number of clusters of galaxies over time, we can figure out how much mass is in the universe. And then the cosmic microwave background tells us about the total energy density of the universe. And they don't equal each other. So adding up the matter density, it's less than the total energy density, and so we are missing something. And in fact, we're missing 70% of what needs to be there. And so that comes from this, this plot was on the previous slide, but so from a combining a set of different observations. So here I have clusters, but other probes of the formation of structure will give you this as well, is very sensitive to the total matter density of the universe. The cosmic microwave background, well, it tells us many things, but one of the fundamental things it tells us is the geometry, the total energy density of the universe. And then we have the supernova, which give us measures of distances. So, and you see, so this plot I'm showing density of matter, density of dark energy. And you can see that there's different dependencies of each of these probes on these two parameters. And then you can take the intersection of them, and you get this pie chart that I showed that tells you, how much of the universe is in the various components. And there's various checks on that. There's other things you can do as well. But fundamentally, this is where we get the how much dark energy and how much dark matter there are in the universe, is by combining these things. Okay, so I talked about this a little bit, but so dark energy versus dark matter. So in fact, right now, the expansion rate of the universe is accelerating, but that wasn't always the case. We have gone through 3 different basic epochs in the universe. The very early universe, before all that matter was formed, was called the radiation-dominated epoch, where most of the energy density was in light. For a lot of cosmic history, we've been in what's called the matter-dominated epoch. So where most of the energy density was in mass, and in fact, so here this is a little so dark matter, the mass wants to collapse the universe. Dark energy wants to expand the universe, and for quite a while, dark matter was winning. But I have whatever mass is in the universe, and as the volume expands, it gets more dilute. So as the universe gets bigger, in fact, the effect of the matter, the effect of that gravity gets less, it gets weaker. Versus dark energy, for example, if it's associated to the vacuum of space, the more space I have, the more of it I get. And so it started in the fairly recent past, actually, started winning. And now, so you can see I get more balloons in dark energy over time. And so now we're in what's called the dark energy dominated epoch, and that expansion is actually accelerating. And this actually is so I'll talk a little bit about the dark energy survey. We have thoughts for the day and a Twitter account if you want to follow us. But there was a cool thought for the day that came from one of my graduate students that was working on this project, where he calculated that the dark energy dominated era may have started, because there's error bars on both of those predictions, may have started after the formation of the first life on Earth. So this was quite recent. So in fact, if we lived in a different epoch in the universe, we might not even be able to see that the dark energy was there. But we now live in this era where we have transitioned to dark energy domination and that accelerated expansion, and so we can see it. But this was pretty recent in cosmic history. Okay, so dark energy, what is it? It might not actually be energy. What we know is that something is pushing out. The universe, the expansion of the universe is accelerating, so there must be something with a negative pressure pushing out. And we know that we are missing most of the energy density of the universe from that cosmic pie chart that I showed. So there are a couple of possibilities. The possibilities include that empty space has a very small amount of energy associated to it that on the scale of the universe adds up to be something large. And that actually makes perfect sense in the sense that in quantum mechanics, we learned that there's an uncertainty where we can actually have particles being created and destroyed all the time. So you can violate conservation of energy if you violate it for a short enough period of time. So in fact, the empty space is not really empty. We think it's like a constant boiling in and out of the vacuum of particles and then those disappearing. So there's good reasons to think that number one might be true. The problem is that if you try to make back of the envelope predictions for how large that energy density should be, it is absolutely the worst prediction in all of physics because the energy density that you would predict is 120 orders of magnitude larger than what we see. So the problem is not that it is there, the problem is how small it is and why it should be that small. Okay, so then there's another very general possibility, which is that, so general relativity has proven correct on every scale we've ever been able to test it on, including with our recent gravitational wave events. And it looks right, but you know, on the scale of the universe, maybe we need some adjustment to our laws of gravity. So possibly we can modify gravity, instead of adding a new energy component, we can modify gravity in a way to explain what we're seeing. Okay, so those are two very general possibilities. Okay, so how do we learn more? So we learn more through experiments like the one I'm involved in, called the Dark Energy Survey, and then LSST, which will be the next generation of this type of survey. So over 6 years, DES is imaging over 1/8 of the full sky. This is a Blanco telescope in Chile. This is the region of the sky that we're observing. Actually, if you go to the southern hemisphere, so these are the large Magellanic Clouds. Those are two of the dwarf galaxies that are actually orbiting us. You can just see them in this picture. And we're doing that using a camera designed specifically for this survey. So in the survey, we have found hundreds of millions of galaxies looking back in time about 8 billion years. So this allows us to probe the history of structure formation in the universe. Okay, so there are different, how do we learn more about dark energy? There are different ways. This is a very basic pie chart showing them. So there are probes that are sensitive to the expansion rate. So for example, I already talked about supernova. So things that give us distances. And then there are things that are sensitive to that growth rate of structure. So how quickly is structure collapsing in the universe? And there are some, like clusters of galaxies, which I'll talk about, that are sensitive to both. And in the Dark Energy Survey, so this is a set of cosmological probes. In the Dark Energy Survey, we do all of the ones I'm circled in red. So we have multiple different probes. They have different sensitivities and different uncertainties in those cosmological parameters. In particular, if we combine things that are sensitive to the expansion with things that are sensitive to the growth of structure, we can actually hope to tell the difference between dark energy and a modification to gravity. Because, for example, you could come up with a dark energy density and a modified gravity that would both give you the same distances to your supernova. But for those two models, you would get a different history of structure formation. So combining them, we can learn more. So you'll see supernova on this list. Other things that we I'll talk primarily about clusters of galaxies, but we also look at weak lensing shear. So if there's mass in front of a background source, the light gets bent, and so it changes the shape of those galaxies. That averaged over our huge survey tells us about all of the structure along the line of sight. Galaxy clustering, so we can do things like, you saw that cosmic web, so if you just do a simple statistic of like, given a galaxy, what's the distance to the closest galaxy to it? Because we have that non-uniform structure, there will be preferred distances. And that tells you about that, it's an average statistic of that growth of structure, is the distances between neighboring galaxies. Okay, so like I said, the Dark Energy Survey does a whole bunch of these. It also does a lot of things that are not cosmology. I mean, the main aim of the survey was dark energy, but we do a ton of other things, including just understanding the evolution of galaxies. But we're finding new asteroids, new dwarf planets, stellar streams, new dwarf galaxies. We've followed up gravity wave events. So there's actually quite a bit you can do with a large survey like this that's not just what I'm going to talk about. So the cosmological probe I'll talk about most is clusters of galaxies. This is what I work on. So I actually, within this large collaboration, I co-chair the cluster science working group. So I'll talk most about how that allows us to probe dark energy. But it's just one of the things that we're doing. So the DES collaboration is a collaboration of over 400 scientists around the world. So you can see we have participating institutions all over the world. So this is a large effort. So this is just a snapshot. So this is our dark energy camera. So we custom designed a camera. It has, I don't know how many megapixels you have in your camera, but I have 570. So it's a camera of 570 megapixels. It has a 3 degree squared field of view. So you can see it's an array of different CCD detectors. And this is the size of the moon on our field of view. So this allows us to cover a large area of sky quickly. So this is what a raw, we call that instrument the dark energy camera. This is a raw DCAM image. It doesn't look very pretty. You can see this is a satellite trail. You can see instrumental defects. You can see like saturated stars with their streaks. Some of these look deeper than others. Some chips look brighter than others. So we have a wonderful custom designed pipeline for reducing this and turning it into the galaxy catalogs that we then use. So we take things that look like this and turn them into things that look like this. So this is Comet Lovejoy actually photobombed us early in the survey. And this is just a beautiful set of galaxy, the beautiful pinwheel galaxy near us, just as an example of what this data looks like when you clean it up. And in fact, they made a whole art exhibit at Fermilab, one of our main institutions, showing some of our beautiful images. Okay, so we have right now we're working on primarily the first 3 years of data. In that first 3 years of data, we have surveyed about 300 million galaxies. This is just the first year of data, and every little point here is the position of a galaxy in our data. So you can see the portion of the sky that we're mapping out there. And this was we have a whole beautiful images channel that I pulled this out of. It's just, it's really fun to look at. But I pulled this out because this, I think, is a miraculous image for showing the whole set of scales that we can see. So here you can see in this one image a Milky Way star, a star in our galaxy, some nearby galaxies, and then most of all of the small points are very distant galaxies. So that's primarily what we're surveying. And then up here in the corner, if you see that green, the small green and red points, that's actually an asteroid. So we take pictures of the sky in different filters, right? And there's obviously a time lag between filters. So this asteroid moved in between the green filter and the red filter. This is just one great example of the wealth of data that we have in the survey. Okay, so my focus, as I said, is using clusters of galaxies. So clusters, like I said, they're the most massive objects that have formed in the universe. They form in the most overdense regions of the universe. And as you can imagine, how many clusters of galaxies you see depends on that balance between gravity pulling in and the expansion history of the universe. So what we do is really just like count up clusters. So we look at, so redshift gives us a time baseline, right? So I can look at things that are relatively close to me, and I can look at some region of space and count up the number of clusters in that region of space. So I have some volume, I count up the number of clusters. And then if I go higher redshift, things farther away, it takes the light time to get to me. So that's farther in the past. So I go farther in the past and I add up clusters, and I go farther in the past and I add up clusters. And it tells me how quickly those clusters are gravitationally collapsing. And that tells me, first of all, very sensitively what the total matter density of the universe is. But it also tells me about the dark energy density because, for example, once we hit that dark energy dominated era where things are flying apart faster and faster, really things can't gravitationally collapse much anymore. So in fact, this is a theoretical plot of like number of clusters in some volume, so number density of clusters versus redshift. So this is time. And as you go back in the past, what do you expect to see? So actually, if the dark energy density is higher, as I go back in the past, I expect to see more clusters because I have some number of clusters today and that I surveyed. And if the dark energy density is higher, they needed to start forming earlier to give me the number I have now. But fundamentally, that's what we're doing, is counting clusters as a function of time. And that tells us about the amount of dark matter and dark energy in the universe. Okay, so how do we do this? So what we can predict, so this is my snapshot of my simulation. What we can predict with simulations of this sort is for a given cosmological model, in some volume of space, how many clusters would I find? What we actually see in our survey is galaxies, and we see galaxies in some angular size on the sky, at some redshift that we can determine with some accuracy. Angular size is not volume. I need my cosmological model to actually turn that into volume. So again, the number of clusters of galaxies depends both on that geometry, that size scale, what that angular scale corresponds to in volume, as well as the rate at which clusters are collapsing. Okay, so this is what we see, and we need to compare it to predictions of this sort. So what can we do? I don't actually see mass. What I see in my survey is galaxies. However, a bigger cluster has more galaxies. So as a proxy of the mass, we can count up the number of galaxies in the cluster. It's actually a better indicator of cluster mass than you might imagine. We call that richness. And, given some cosmology that I am going to compare to, I can turn my, survey angular size into a volume, and then I can compare to my simulation, to my theory. So what we're doing is actually measuring, so this is number of clusters as a function of richness, which is my proxy for mass. So this is what I see. I count up number of clusters in some volume as a function of richness, and then I need to turn that into number of clusters of a given mass in a given volume to compare to my theory. Okay, so step one to even get this far is I have to find clusters. How do I find clusters? We find clusters based on what's called the red sequence. So this is a very prominent example with a very local massive cluster called the Coma cluster. So we are helped, if you look at my picture of a cluster here, you can probably pick out for this cluster which galaxies likely belong to that. They're all similar color, right? So the galaxies in the clusters, first of all, are all at the same distance. They're all at the same redshift, which gives them a similar color. They also tend to be the same type of galaxies. And so if I just take a region of space and I plot up how bright my galaxies are compared to what color they are, I get this sequence, what we call the red sequence, where I have galaxies of all different brightness but of very similar color. And those are the ones that belong to my cluster. So I can find clusters by this overdensity of galaxies, both in spatial position, they all live close to each other on the sky, but also overdensity in terms of having similar color. So that's how we find clusters. So step two, so we have to determine the position of the cluster. We also need to know its redshift. We need to know how far away from it is. And here, we're really helped by the color of that red sequence. So we don't have spectra in our survey. We just have images. We have images in 5 different filters, so 5 different bands. So it gives us a spectrum with like 5 bins. And based on that, we can estimate a redshift. But in clusters, we can actually do quite well. We can get the redshifts to 1% because we have that red sequence of galaxies all at the same redshift to work with. So that allows us to see how far away from us they are. And then we find the position of the cluster based on the fact that there's essentially always a big galaxy at the center. So the algorithm that finds these clusters looks for overdensities of galaxies around central galaxies. And then what we do is for every galaxy in that field, we assign it a probability of belonging to that cluster based on, based on both its color, so does it match the red sequence for this cluster, its distance, and also, how close is it to other galaxies. So every galaxy then gets a probability of belonging to that cluster, and the sum of those probabilities is actually what we use as the richness. So it's our likeliest number of galaxies in the cluster. And then, so we have richness, so we have number of galaxies, and then we need to calibrate. We don't have to get masses for every single cluster in the survey, but we at least need to be able to calibrate. I found a richness of 30. That means a mass of something. And we do that using lensing. So the depth of the data of our survey is not enough that we can do lensing measurements for every single cluster, but we can stack them. So we take a bin of richness, and we add up all of the observations, and we look at the lensing signal. So this is the fact that, like, background galaxies, this is not strong lensing, huge arcs or Einstein rings. This is just like, I have a galaxy in the background of my cluster, and it was some shape, but because the light passes through my cluster, it gets stretched a little. So it's a little more elliptical, it's a little more elongated than it otherwise would be. And that is a teeny effect, but if we have enough background galaxies, we can measure the mass. So we do that in bins of richness, as I said, and we're able to then get the relationship between richness and mass to a total uncertainty of only 5%. Now, we are unfortunately at the part where we are not dominated by statistics, how many clusters we have. We are dominated by uncertainties, systematic uncertainties like in our measurement of redshifts and other factors. So going forward, this is for the first year of DES data, what I'm showing. Going forward for year 3, we're actually putting a ton of work into getting down our systematic uncertainties to the point that we can really take advantage of our growing statistics. Okay, so now what this gives us is, okay, I have a richness of 30. It has an average mass of a few times 10 to the 14. But it doesn't tell me, I also need an error on that. So what I really want is a richness of 30 is a mass of 3 times 10 to the 14 plus or minus, 1 times 10 to the 14. I need the error bar too. So what we need to know is what's the scatter in that. So what we can use is observations at other wavelengths. And in fact, so this is a paper by one of my graduate students who just graduated. So this is a lot of the work that our group has been doing, is we can follow up clusters in other wave bands. In particular, in this case, we're using X-ray. And so in X-ray, what we see is that the cluster is full of, so it's a huge gravitational potential well. That cluster collapses, and when it does, it brings in everything in that region of the universe with it, including the diffuse gas throughout the universe. And it's so massive that it heats that gas up to something like 10 to the 8 Kelvin, hugely hot. And it is so hot that it radiates an X-ray. And so the X-ray temperature, the temperature of that gas that we can measure in X-ray, is actually a sensitive probe of how deep that potential well is, so how much mass is in the cluster. So X-ray observations, we can't get, so in DES we're going to get tens of thousands of clusters. It's too observationally expensive to do tens of thousands of clusters in X-ray, but we can follow up hundreds of them. And that allows us to look at richness versus mass and look at the scatter. So this is how we can get that error bar. So this is how we do that mass calibration. So we take what we can see in the survey, which is richness, and we turn it into what we can predict, which is mass. Okay, so this is an example. So this is using the Sloan Digital Sky Survey, which is a previous survey like DES. Covered a very wide area, but it wasn't as deep, so it didn't go back as far in time. So kind of as a practice round for the cosmology we're doing with clusters in DES, we did the same exercise with Sloan clusters, found in the same way. And here's some of the results we've gotten. So this plot just shows that so the gray is our error bars for Sloan, compared to other surveys. So we have similar size errors, and we're agreeing pretty well. So here's some contours. So this is matter density. This is a parameter that tells us about the amplitude, like how big those early density perturbations are. And this is the Hubble constant. And so what you can see is some of our contours compared to in the yellow, well, sorry, this is combining different things. So clusters plus Planck plus galaxy structuring are the yellow, giving us tight constraints on these parameters. So this was done with not quite 7,000 clusters, back to redshifts of 0.3. It's just like a billion years in the past. And it's consistent with everything before it, but not yet winning in terms of statistics. So what we're working on now, and unfortunately I can't show you results, the paper is essentially done and going through internal review in the collaboration, so it's not public yet. So what I'm showing you are not the actual results. It's just an example to show you how great they're going to be. So coming soon this is the clusters from just the first year of the survey. Eventually we'll have 6 years, so we'll do even better. Using a similar number of clusters to what I showed before, but going to significantly higher redshifts. So the gray, so again, this is amplitude of perturbations versus matter density. The gray is what the Sloan results that I just showed. The blue is actually a set of all of the other, well, except for the supernova, several of the other measurements we can do in DES, so the galaxy clustering and the lensing. That's the red. The blue is the size of the error bars that we expect to get with clusters in year 1. So you can see that, now these aren't in the right position. This is what's called blinded. So we, because we want to be good scientists and not massage our results to be what we want them to be, we do all of our analyses blind. So that means that all of our data gets shifted by the computer by some random amount that we don't know. So that we can't plot up contours like this and be like, oh, it's not agreeing with, the Planck results. Maybe I should remove these couple of weird clusters and that, yeah. So these are blind. So the position of these contours is not accurate, but the size is. So compared to the Sloan results, we will be much more sensitive. And in fact, actually, the clusters alone has a similar constraining power to a combination of 3 different probes altogether from the DES data. So that is coming soon. Since I can't show you that, I will show you the year 1 results from that combination of lensing and clustering. So these are published. And so, okay, so from, again, matter density versus amplitude, the DES combined constraints from lensing and galaxy clustering are in blue. The Planck cosmic microwave background constraints on these same 2 parameters are in green. The combination of the 2, when you add them together, is the red. So a couple things I want you to take out of this plot. So first of all, we are now getting to the point where our surveys of structure in the late universe, so those galaxy surveys, have the same constraining power on some of our cosmological parameters as the cosmic microwave background. And this is just year 1. So similar constraining power to Planck. And then when we take ours and we combine it with all of the other things out there, so we take DES combined with Planck, combined with baryon acoustic oscillations, this is galaxy distances, and supernova, everything is consistent with a cosmological constant. So far, everything we've seen shows that the universe really is consistent with having this constant energy density associated to the vacuum of space. And then there's this interesting, you can see that these don't quite line up. They are not far enough apart that we call them inconsistent. But there is an interesting, so here, this was DES. This is DES plus other, like supernova, all other, what I'm going to call late time measurements of cosmology. And this is Planck by itself. So this is that very early universe cosmology. Now the tension is only maybe a couple of sigma, so we can't say for sure that this is interesting, but it's possibly very interesting that in fact we take our model for cosmology from that very early universe down to today, and they're not quite agreeing. So if this tension turns out to be real, it means that we actually do need some adjustment to our, just lambda cosmological constant cold dark matter model of the universe. One possibility would be that we need an extra species of like neutrino. So we need some other relativistic particle. There's other interesting possibilities. So it's not enough to say anything yet, but it is true that pretty much every, survey like every survey of the local structure is always offset in this direction from the Planck. So that's interesting. Okay, so it is 5 o'clock, but I think this is pretty much my last slide. So that was my cosmology. I did want one slide on other things that we can see in DES. So this is that the DES image of that gravitational wave event, that first neutron-neutron star merger. So we were one of the very first telescopes to see. So that's before, and this is after. You can see it. This is Elon Musk's Tesla Roadster. Yeah. And then the video that went by pretty quickly, let's see if I can, you know what, I'm going to go back and then I'm going to make it play again. Okay, so this is trans-Neptunian objects, things in the Kuiper Belt, so asteroids and dwarf planets, a whole collection of them orbiting through our survey. So tons of science that we can do that's not just cosmology in DES. Okay, so just to summarize, a few takeaway points. So the dark energy survey is giving us precise constraints on the late time structure of the universe that's starting to rival the cosmic microwave background. And we're just really have done the early data. There are a wide range of probes that currently all agree on, just a cosmological constant cold dark matter model. We have found nothing to say that dark energy is different from a cosmological constant. However, there's some interesting tension. And the future is very bright because we have upcoming next generation surveys that are actually not that far away, just a few years away now, both from the ground and in space, that are going to do even quite a bit better than what we have now. So I will end there with this pretty picture of the Blanco in Chile. Thank you.